So from A, 0, 0, 1 would be getting how much? Let us see. From A, it's going to be 12 with probability Q, and 0 with probability 1 minus Q. So it's going to be 12Q here. From B, it's going to be 11. That happens with probability Q. So 11Q plus 1 multiplied by 1 minus Q. This is 1 plus 10Q. C is going to be 10Q plus 4, 1 minus Q. This is going to be 4 plus 6Q. And D is going to be 9Q plus 6 multiplied by 1 minus Q, and this is going to be 6 plus 3Q. It's difficult to compare them. So what is the best way to go about it? Have an axis and there draw, let us say here is, of course it is not to the scale. My drawing is also not that good and I don't want to spend lot of time drawing it. So when we do 12Q, let us say it goes till here. So 12Q is going to be like this. This is 0, this is 12. What is happening with 1 plus 10Q? So to save time, I have plotted the payoff from A, that is 12Q given by red color, B 1 plus 10Q given by B color, and C, that's 4 plus 6Q navy blue color, and D 6 plus 3Q purple color versus Q. On y axis we have Q, and so we can see from this graph it is very clear. This point is, you should check, is 2 by 3. One can check what happens the payoff when player 2 is mixing between x and y with probability 2 by 3 and a by 3. From this formula it is 8, because 12 multiplied by 2 is 24, divided by 3 is 8. B by 2 by 3, it's going to be 1 plus 10 multiplied by 2 by 3, that is roughly 7.667. C, you get 4 plus 6 multiplied by 2 by 3, this is also 8, and D will also give you 8. So A, B, C, D, all they, sorry, except B, they all cross from this 2 by 3 point. Okay, so we can take further, we can write here, because it's good idea, every time we will have to come back. When player 2 is playing, let us say we should get the best response of player 1 against player 2 playing Q. What does it mean? That if player 2 believes that player 2 is playing X Q out of Q percentage of time and Y is 1 minus Q percentage of time. So this is what we can say, this is equal to D if Q is less than 2 by 3. This is on top. What we should put bracket, because it is correspondent, and A except B, because B is always lower, B is never the best response. So at 2 by 3 best responses are A, C and D if Q happens to be equal to 2 by 3, and the best response is simply A, this red color, if you know A, if Q is greater than 2 by 3. So we get the best responses. The only thing is, from here it is clear that B is never a best response. So what we have just figured out in the previous video, that if an action is never a best response, it has to be dominated, and that we can check. Can we take, for example, let us take a mixed strategy that gives 3 by 4 weight to A and 1 by 4 weight to D, and check this, how does this mixed strategy does against B. So if player 2 is using X, what this strategy would give? 3 by 4 multiplied by 12, because this box is going to happen with 3 by 4 probability, and plus 1 by 3 probability multiplied by 9, this box is going to happen, sorry, 1 by 4 you will get. So 12 multiplied by 3, 36, plus 9, 40, 45, divided by 4, definitely larger than 11. And how about against Y? This is 0 and here is 6. So 6 multiplied by 1 by 4, 1 by 0.5, which is greater than 1. So clearly this 3 by 4a plus 1 by 4 d dominates b, and that's what we have learned in the previous video, that never a best response gets dominated by a mixed strategy. We cannot do such things for other C, because C is at least a best response when Q is equal to 2 by 3. So we will proceed from here. Now let us solve the game. Rather than focusing on the complete game, we should focus on the reduced game in which we have eliminated B by elimination of iterated elimination of dominated strategy. First, I want you to make sure that you figure out there is no Nash equilibrium in which player 1 and player 2, 001 and 002, both are playing pure strategies. I will not get into it, but I request you to go about it. Now let us think, do we have any mixed strategy in which one player is mixing and other player is not mixing? This is one way to go about it. So here is of course Q and here is 1 minus Q. And we have already seen that if Q is equal to 2 by 3, the best response from player 1 is all A, C, D. So if player, what does it mean? If player 2 is mixing between x and y with probability 2 by 3 and 1 by 3, then player 1 will get same payoff from A, same payoff from C and same payoff from D. It means player 1 can also mix between A, C and D, but let us first focus on a pure strategy. This was 2 perhaps, let me check that this was, yes, this was indeed 2. So if player 2 is mixing here, so of course what we need to make sure that in this case player 2 should be getting the same payoff from playing X or playing Y. So of course here player 2 gets the same payoff because in both case it's 2, and no matter how he mixes, if player 1 is playing C, then it will work well, because if player 1 is playing C, what is the best response from player 2? Player 2's best response is both X and Y. Okay, these are the best responses from player 2. So player 2 can use any, let's say QX plus 1 minus QY, but if he uses any Q, then payoff is going to be 11Q plus, and this is going to be 4 multiplied by 1 minus Q, and which may not be the same as A and C. But if Q happens to be equal to 2 by 3, then we have figured out that C gives 8, A gives 8 and D gives 8. So we can have a Nash equilibrium in which player 1 is playing C and player 2 is playing 2 by 3 X plus 1 by 3 Y. What we need to focus on, that player 2 needs to mix using 2 by 3 and 1 by 3 probability for X and Y to make player 1 indifferent between A, C and D, and then all our best responses. So this is, can we figure out all Nash equilibrium? Yes, we can obtain. First let us note down the things that we have learned about these players, that what's happening in the game. In this particular game, what we have is, let me draw this, that player 2 is definitely mixing. You can ask me how did I figure out? I asked you earlier that figure out all pure strategy Nash equilibrium. You can check when player 2 is playing a pure strategy. You can check from here also. We had obtained that if Q is equal to 1, then best response is A and A's best response is Y. So that's where you cannot have a Nash equilibrium. And when Q is equal to 0, it means player 2 is playing Y. Best response from player 1 is D, but if player 1 is playing D, best response from player 2 is playing X, that is Q equal to 1. So there are no such equilibrium in which Q can be 0 or 1 corresponding to pure strategy of player 1. So player 2 is definitely mixing. So when player 2 mix, when her payoff from x and y are equal. So let us say player 1 is mixing using PR 1 minus P minus R. In this situation, player 2's payoff from x and y both have to be the same. Let us look at player 2's payoff from x is 0 multiplied by P, 2 multiplied by R plus 3 multiplied by 1 minus P minus R. This will be equal to 3 minus 3P or minus R. And how much y will give? Y will give 6P plus 2R. These two have to be equal. And from here we can get 3 minus 3P minus R is equal to 6P plus 2R. What do we get here? Let us say that everything is brought to the other side. It will become 9P, it will become 3R is equal to 3, or we can say 3P plus R is equal to 1. What do we get from here? That 3 times of the weight of player 1 and plus single time weight of player 1 playing C, the sum should be equal to 1. Does it fit in this? Can we do that? If R is equal to 1, that will make P is equal to 0, and when P is equal to 0, 1 minus P minus R will also become 0. So this is very valid as per this definition also. What it tells us, there are many such equilibrium in which player 1 0 0 1, let me use a different color, 0 0 1 is playing P multiplied by A plus R multiplied by C plus 1 minus P minus R multiplied by D, and player 2 is playing by 2/3 x plus 1/3 y, such that 3P plus R is equal to 1. And this includes this particular equilibrium, because then it is satisfied when we put R is equal to 1, this becomes equal to 0, this becomes equal to 0, and this equation is also satisfied. So there are so many infinite equilibrium here, and all equilibrium are characterized. Just to tell you what are the principles that we have used, that if one strategy, one action is never a best response, then it is a dominated strategy, strictly dominated strategy. We can remove it from the game, we can get the reduced game, and we can solve that reduced game, and the equilibrium that we get would be applicable to the larger game also. And here we have used that if player is mixing between two or more strategy, all those strategies which have positive probability in the mix should be giving the same payoff given what other player is doing. And if a player is not using a particular strategy in mixing, there are two possibility: either this strategy or action is giving exactly same as other strategy being used in the mix, or this strategy which is not being used gives strictly less than all other strategy which are being used in the mix. Like for example, if we look at that C 2 by 3 x plus 1 by 3 y, in this case given player 2 is playing 2 by 3 x plus 1 by 3 y, A would also give as same as C, D would also give same as C, but we are not using A and D in this equilibrium. What is the reason? Because A and D would give exactly the same. So if we need it, we can use it. If we don't, we would not use it. But we would definitely not use B, because B of course gives less than C. So I hope this example is clear to you. I urge you to solve some problems from Joel Watson book, from Osborne's book. There are so many game theories book. It's good idea to solve some problem. It would always be helpful. We are next and the last video on mixed strategy. We are going to look at the interpretation and justification of mixed strategy equilibrium. See you in the next video. Thank you.